All right, perfect. Well, then let's get started then. Thank you so much, everyone, for joining on the call today. We are the CRC Engineering and Innovation Working Group, and this is our quarterly stakeholder meeting. So just to start off, this is going to be our agenda for today. So we'll start off with some quick intros and updates on our working group, go into an icebreaker to understand really the demographics of the people on this call, and then we'll go forward with the meat of the presentation by David Schmidt and April Hays. Okay, so just to begin, the vision of the Engineering and Innovation Group is to foster a community to facilitate innovation for coral reef restoration. So we like to gather all different types of stakeholders, whether it's restoration practitioners, engineers, manufacturers, researchers, academia, to really be on the forefront of engineering and innovation for coral restoration. We are definitely facing dire times right now with increasing temperatures and massive bleaching throughout Florida and the Caribbean. And so it's really just fortifying the need and the urgency to further innovation in the coral restoration space. So while it can be a depressing time to be in this field, it's also a time of so much motivation and inspiration to be around technologists and innovators that are really pushing this forward to save coral reefs on a global scale. With that said, I wanted to just go forward with what the stakeholder meetings are. So these are general meetings to rally the community and to increase opportunities for collaboration and networking between stakeholders. So like I said, we have restoration practitioners on the call, we have engineers, innovators, research and academia. And so really we just want to be a group that can gather and we can speak on ideas and really start to brainstorm ways to improve nature-based solutions in the marine environment. So with that said, these meetings will be a forum to share high-level updates on the EIG network and then the Coral Restoration Consortium as a whole. It's to host presentations from practitioners that are working on all sorts of interesting fronts in coral restoration and to network with others. I wanted to just go in with Coral Tech. It's one of our largest innovation initiatives with the EIG. It is now officially live where you can submit projects for coral restoration. We're hoping to have more of a broad introduction into Coral Tech soon. And so with that, I'm just going to keep it very high level for now and keep moving through this. And in terms of announcements, you might recognize that I'm a new face. I'm the new interim chair for the Coral Restoration Consortium. I'm very happy and grateful to be here. And of course, I'm always taking just new ideas. And so I'm just, very happy to be spearheading this group. And of course, if you know of any future stakeholder presenters that you'd love to see on these meetings, please email our secretary, Megan Ramirez at crceig@gmail.com. Oh, just one second. Oopsies. Sorry, I live by a train track. But yep, so that's really just our main introductions right now is just who I am and then Megan, who can speak on just more of her secretary roles. So those are updates. And now with that said, I'd love to just get more of a demographic on who is on this call. And so if you can click on this link, or if Miles, if you can just drop in and put the URL here into the chat, that would be great.
It is already there.
Oh, it is. Okay, perfect. So so if you
I just dropped it in.
Great. If you want to click on this link, you'd be able to create a sticky note with your name, location, and focus of work so we can see who's on this call.
On the left-hand side of the screen, there's going to be an option for a sticky note. Because if you click into one of the notes that's already there, it's going to steal it from somebody else. So try and create a brand new one over on the left-hand side there, and then you can move it around to the grid that we've created.
Perfect. Great, so I'm gonna do this now.
And the hope was that folks could share in there, put your name, where you're at location wise, and the focus of your work, just to help others in the room know kind of who all we have here and be able to just get a better idea of that and maybe potential connections for the future for everybody.
Great. So I'm seeing people as coral restoration practitioners spanning the Caribbean, Mexico, Bonaire, Florida. We have engineers on the call from Boston, from Philadelphia, and a few other places. Let's see. Very cool. Let's see, this is sort of thing.
That's weird.
With these.
That's awesome. That's awesome.
Great. Yeah. Very cool. Yeah, so we have people from all over on this call, which is really exciting to see. Amazing. And while we're going to keep working on this, you can always come back to this link and see who's on these calls. And if there's someone in particular that you'd like to be connected with, we'd be happy to share those contacts with you as well. Great. So with that said, I'm going to keep moving forward. Okay.
Oh,
Okay. So with that said, it is my pleasure to introduce Mr. David Schmidt and Mrs. April Hays. David Schmidt is the CFO of Mussel Polymers, as well as the president of Vertical and Reef. He is a chemical engineer by trade, and now he is working in the adhesive space. Mrs. April Hays is a business developer on the Reef vertical, as well as a dental vertical. She came from the dental piece of Mussel Polymers first and has transitioned into the coral restoration space. So with that said, I'm very excited to present David and April, and I am going to stop sharing now so you can take over.
okay.
Thank you very
That's
much.
Of course, thank you.
All right. Well, welcome everybody. We are very, very happy to be here, and this icebreaker event was a good one for me because I've recognized a number of names that started to pop up there, and we've spoken to many of you in the past, and would love for you guys to contribute if you'd like, but. And I see some new names on that icebreaker that I would certainly like to connect with as well. So we've got some time here, and April and I thought it would be useful to go through the Mussel Polymers story, bring it down to various applications, chemistries, bring that down into the formation of a coral adhesive product, and then kind of finish up in new product development so that we can kind of tell you a story about our journey here. And what we're presenting for you today is a biomimetic adhesive system for reef restoration. So we have April Hays with me, and we have myself. So what is Mussel Polymers? Mussel Polymers was formed in 2020 in February of 2020, only to get shut down by COVID. And so we really got active in the fall of 2020. But we are the world's leader in catechol polymers, catechol chemistry. And these chemistries have broad-ranging applications to include biomedical and industrial and defense, and so on. But what we're really trying to do is leverage the reason why mussels stick to coral reefs, and yet it takes a jackhammer to get them off. So here's the star of our show. We've got the blue-footed mussel. And the blue-footed mussel sends out a tendril, and on the end of that tendril is a foot. And within that foot is when the mussel wants to stick to a coral reef, it excretes a protein. Within the protein is an amino acid. Within the amino acid is a catechol compound. And this benzene ring with 2 hydroxyl groups, and I know I got really above, but that is the catechol compound that is responsible for underwater adhesion. Now, many groups have tried to synthetically make a catechol, and they've been unsuccessful in doing anything at scale. And that's where Mussel Polymers came in. We took a very, very different approach. Instead of trying to extract that mussel glue or copy that mussel glue, we ended up doing a biomimetic, or we are copying something that happens naturally in nature. And we did that by taking a polymer backbone and attaching catechol molecules across that. And that is what this molecule on the right-hand side, nature-inspired, it's simple, it's powerful, and it's safe. The company, as I said, is working on adhesives. And when we think about adhesives and adhesive chemistries, you've got epoxies and polyurethanes and acrylics and methacrylates and so on and so forth. One of the incumbent products in reef is the cyanoacrylate, or the superglue. These industries are heavily used. They're mature technologies. They have intrinsic problems when wet, and there's a lot of toxicity associated with these things. But the reason I'm singling out cyanoacrylate is that superglue was invented in 1942. What we are working on at Mussel Polymers is the next generation of adhesive chemistry measured in decades. So what we're really doing is launching multiple applications off of a platform using biomimicry as the approach. Okay, so these catechol polymers have a wide range of applications, and I'm just going to go through this very, very quickly, but this underscores just how broad this category is. You've got catechol polymers that are responsible for adhesion. There are self-healing properties of these. There are electrical properties, anti-corrosive. In our dental space and in our biomedical space, we have learned that they have cellular effects and they've got antimicrobial effects. In dental, we have learned that these compounds actually regrow enamel on people's teeth. So, I mean, it's a fascinating polymer to work with. And really what this is it's a successful, repeatable commercial development process that we can work on at scale. And to give you an idea, for those of you who are watching, this actually is the polycatechol styrene. It is a powder. It's flaky. It takes quite a bit to make this, but this material is super highly functional. So as a company, we could go bankrupt chasing all of those categories. And so what we did is we took the company and we divided it into three, looking at industrial, coatings, and dental and biomedical. We looked at how sustainable this is, how fast we can get to revenue, what the regulatory timelines are, and we can gain traction and migrate to other value applications. And the coral and reef falls right into this short-term timeline. So what we're talking about here is our CTAC adhesive, which is over here on the left-hand side of the screen. This is our launch product. This was our first product that is outside of the laboratory. And we're going to talk a lot about this in the next few minutes. And this is where we are on our development timeline. We've actually launched this product. There are people that are buying this product, and there are several groups who are using this product. We are mostly in the aquarium hobbyist segment and are entering the coral reef restoration segment and broadening that. One of the other applications of this particular product is submarines. So the U.S. Navy is testing this in open water situations while they are using these products to repair submarines without ever bringing them into port, which is pretty fantastic. And it's exactly the same product with the same formulation. So this gets us to our mission statement, really, for the CTAC. April, do you want to talk a little bit about this?
Yes. So the purpose of CTAC is to help with coral restoration. And as you can tell, it can do a whole lot more. What we're really aiming for is healthy ecosystems that include societies, buildings, not only restoration, but medical. There's so many applications that we can reach. And so we're starting in coral because it is living. There is a need right now, and it directly affects economies like fishing, like clams, and also refencing for waves. And so this has been a huge backbone behind building CTAC out. We've gotten really great support from our restoration practitioners who have been giving us feedback on CTAC and how it's working and how it's not working for them. And this has been really helpful for us in creating next version development of CTAC so that we can further be able to help communities that are affected by changing climate.
Right. And
go ahead, Dave.
no, you've been.
Okay. You all know about the coral decline and the collapse happening. So CTAC directly addresses these areas with not only rebuilding coral and coral substrates, whether biological or artificial. It can help with wave reduction. Works really great with things from wood to cement to glass. Plastic, that's its own little anomaly we can go into later. But there's lots of substrates that CTAC adheres very well to and can address right now the coral decline that's happening.
Right. And this is a topic that you all are very, very well familiar with, and we don't have to dwell on what's going on out there. But different people throughout the communities have to come together to solve all these problems. We went out and recognizing that we're an adhesives company, we started looking at government grants, and ultimately, through several selection processes, we applied for a NOAA grant, and the need was really for a new coral adhesives. And this is a direct quote from Tom Moore when he was part of the NOAA Coral Reef Restoration Program Manager at NOAA, who was our sponsor for this SBIR grant. And, you know, very simply saying, if we could find a more effective adhesive, it has the potential to increase the rate of outplanting quite literally overnight. And so when you there's obviously other challenges to scaling coral reef restoration, but this is one where we could have an impact on doing just that. So if we think about this as an anecdotal sort of way, when you're outplanting, as you all know, if you're doing coral gardening or so, once you've got your mature segments and you're trying to actually outplant on a reef, you commission a dive boat, you commission a captain, you commission divers, you jump over and start planting your corals. A diver can effectively plant somewhere between 6 and 10 corals in a dive, or at least that's what we have learned. And if we could effectively increase that rate of outplanting, we could have a material effect. So said anecdotally, the diver runs out of air before he's planted enough of the reef to make a difference. So our working hypothesis was, how could we get to a point where we would squirt, stick, and go? So what's the problem that we're actually trying to solve here? In the coral gardening, the microfragmentation space, you start off with a live coral and you cut those. It's very, very similar, as you all know, to propagating plants. You take a fragment off of a living coral, you attach it to a substrate. That's usually done with cyanoacrylates. Then those are nurtured in some sort of optimal environment. And once they're large enough, they go out to the reef, and they typically are using epoxies and now hydrostatic cements, but they're typically using epoxies to attach these fragments to the reef. Now, in both these cases, you've got poor wet adhesion, and there might be some people that disagree, but this is at least what we have found. In wet environments, the cyanoacrylates cure way too fast, and in open ocean, the two-part epoxies actually don't adhere quite at all. It's a mechanical interlock with the nooks and crannies in a coral reef. So the practitioner actually has to mold that particular epoxy and wedge it into the reef while it's curing. Another problem that people are dealing with is toxicity and irritation. So the cyanoacrylate has a tendency to burn corals at that point of interface where the coral fragment is attaching that substrate. To as much as a third of that coral fragment you'll have necrosis and burning. Similarly, we've got irritation with two-part epoxies. When you mix two-part epoxies together, from a chemistry standpoint, you release amines into the water. And I'm sure several of you have experienced this directly. This cloud that tends to form as you're mixing these two parts together. That cloud are amines. And as you may know, amines are toxic to fish and toxic to coral. Now, in an open ocean situation, those ultimately get diluted to infinity, but still you're washing amines over living tissue. So there was this need to scale with a non-toxic wet binding adhesive. And what we've been working on with this polycatical styrene seems to be a perfect fit. And so then we kind of said, well, what sort of scale of material would actually be needed to solve some of these problems? And the answer is industrial scale is required for this. It's not laboratory scale, it's industrial scale. So we had partnered up with several of the restoration communities, Moat being one of them, CRF being another one of them. And in 2019, roughly 1% of the attacked reefs through the coastline of Florida was restored. And for that alone, you're going to need tons of material in order to address that space. Well, Moat and CRF, they outplanted roughly 60,000 coral fragments in 2019. Let's put this in scale. If you take a microfragment, and assuming that each microfragment needs a square foot of material, 37 million fragments is a fragment area of 1.3 square miles. Well, what is 1.3 square miles? 1.3 square miles is the area of Central Park in Manhattan. Well, wait a minute. If we go back and they planted 60,000 coral fragments and 37 million is the size of Central Park. And what's actually going on here? Well, to put this in perspective for some of the other people that are on the phone that may not think about the Northeast of the United States, Central Park is about 1/5 the size of the King Solomon Park in Saudi Arabia, and it's about 2 times Centennial Park for those that are in Sydney, Australia. So, so to put this into perspective, for the Florida Reef area, if Central Park, 37 million is 1.3 square miles, the commitment along the Florida coastline is the equivalent of the 3 boroughs of New York City: Brooklyn, Manhattan, and the Bronx, and that's 231 square miles. Well, of course, there are other areas throughout the world, like the Great Barrier Reef. Well, how big is the Great Barrier Reef needs for reef restoration? It is 134,000 square miles. So to put this in perspective, what's being done today is less than Central Park in Manhattan, and the need is greater than the entire Northeast of the United States. To kind of put that in, it's huge. So there is absolutely a need for a better ways of outplanting, and that could be robotics, that can be cement structures, and for what we're talking about here is adhesives. This particular picture, that slide that we're looking at, is actually this polycatical styrene applied underwater onto limestone tiles in artificial seawater, and we're applying them with a little tiny brush. And so this black that you see on top of this tile is being applied underwater, and they are being sandwiched together with and limestone is calcium carbonate, which is also what reefs are made of. Now, on our right side of the screen, we have a 10-pound weight and a clamp, and this person is holding on to this limestone tile with his hands. So this was applied underwater, and approximately 1 hour later, it was pulled out, and with this simple strength test. And I'm going to hit play, and we're going to see what happens. Back to here. So you can see where he's holding on to that. We've got some initial good grab for a polycatechol styrene as a bulk adhesive. It's pretty darn good. All right, so we were, and these were our activity sets largely through 2020 and 2021 underneath this SBIR grant sponsored by Tom Moore. And one of the deliverables of that grant was to come up with a prototype adhesive system. So we started formulating with that particular polycatechol styrene with the substrates, the outgrowth, the attachment to the live rock, and ended up with a combination product of a polycatechol styrene and a bulk polycatechol, a bulk adhesive, a commercial bulk adhesive. And that's what CTAC ended up being. So we end up adhering to a wide range of wet surfaces, even underwater. There's little surface preparation that needs to be done. In fact, we have been finding that in certain circumstances, we can actually penetrate through the biofilm and no preparation is actually needed. And we have reasonable setup, rapid setup. The question is, can we scale this? And can we to address that massive need out in the marketplace? So the target profile, if we could hit each of these metrics, we would in fact have an adhesive that could go out onto a coral reef. And these were the metrics defined by NOAA. So it had to work in seawater. It had to be negatively buoyant. It had to be sticky and tacky, and both grab the substrate, which is a plug of some sort, as well as the coral, which is tissue. It had to be able to be dispensed. We could work in volumes of as little as 1 milliliter or up to as much, greater than 20 milliliters. We needed full cure, and it needed to last at least a year, and we hit all those metrics, and we came up with these products of CTAC. So CTAC is a sticky and tacky underwater adhesive that is our bulk adhesive. And if I squeeze through some of this adhesive, I've got something that is super sticky and tacky that I can go underwater, and it is still super sticky and tacky, to which I can attach that to a coral plug of some sort, and let's see. I'm going to fish out a dead fragment out of this. So a dead fragment of coral, to which I'll just literally stick in there. And, there it is. It's literally, now this is not cured. This will cure in the presence of moisture. This will cure underwater. And no, I don't need that much adhesive. I can actually wipe a lot of that stuff off. Okay. But so that kind of gives you an idea of this prototype system. And so while we're still scaling the polycatechol styrene, we do have the bulk adhesive, which also is sticky and tacky underwater. And in 2023, we came up with, we launched a product into the aquarium space. It is the CTAC product in different formats, in a tube, in a standard caulk tube, and in a syringe that could be either manually dispensed or in a pneumatic dispenser of some sort. And that's what we're here to demonstrate today. So April, I'm going to move on the slides. And how does this CTAC product stack up to the next best alternatives?
Well, as you saw, it's sticky and tacky underwater. It grabs to coral. We've had restoration practitioners have great success in the lab with putting on plugs, doing rockscaping, pre-seeding, where it's easy to dispense. Of course, you gotta puncture the hole, which we realize we need to put a label on for, because people are like, it doesn't work. But we can do it, we can apply underwater and above water. And it is works. We've gotten feedback that it works better than epoxy and super glue in the lab. And
right. And so obviously a lot of these other adhesives, there are good uses for all of these other adhesives. And what we're trying to do was eliminate any of the undesirables with specifically the next best alternatives being cyanoacrylate and epoxies. A lot of times the cyanoacrylates, as soon as you take that tip and you put it underwater, it will cure instantly, and you cannot dispense that cyanoacrylate. A lot of times, while you do have structural support with epoxies, you don't have grab per se. There is a toxicity profile with a lot of these, and so we ended up with this go-to-market product, which was good, and yeah, so we've done some successes. I mean, we've had good success in the retail hobbyist space, where people are doing a lot of microfragging, and where CTAC works really, really, really well is in this microfrag market. But we've also had various successes in open ocean trials, which we're working on. And April, you want to talk?
yeah, National Taiwan Ocean University, they got back to us and they had outplanted 21 frags that were grown on stakes about the size of your hand in April, and they had gone out into the open ocean, drilled some holes, put their stakes with their frags on it, and of course it was filled with CTAC. They normally use super glue, and a couple weeks later they had the Moar typhoon hit, which was a Category 5, and they came out a month later to assess the damages and see what what was left, what happened, what stayed, what went. And what they found was that everything that had been placed with CTAC had held, was still firmly in place, wasn't wiggling, moving, nothing. It was to their amazement very strong, and there was some branches that broke, but all of the bases where the CTAC was applied wasn't moving at all.
Right, right. And that's a great case study. The team out in Taiwan, they're perfectly willing to talk to anybody who would like to share. So I'm happy to connect you guys with them at any time. But it really was a good success story where they went out and so in their environment, they are repurposing abalone farms along the shores. Now, these abalone farms were cut into the coastline, so it's actually seawater that fills these ponds, and they nurture their coral in these basically swimming pools that are cut into the side of the reef. They went out into the open ocean and planted several very large acropora heads, and that this large super typhoon came through, and as April said, they had success. So that was fantastic. We have another group.
It was success too when they had this last typhoon that came through. I forgot the name, forgive me. It knocked over some of their tables and their pools that they use for culturing, and they put, when they drilled the tables down, they applied CTAC, and they figured they had enough success with the first time, why not do it again?
So what are you saying, April? Are you saying that they used it as a industrial construction to anchor their tables?
Yeah, they anchored it with metal bolts into cement. Yeah.
That's interesting. So in the Caribbean, we have another group, a repeat buyer of materials, and their quote was this works so well to attach their coral fragments both above and below water, and it worked. And their quote was, "This works better than anything that we've worked with." And they were specifically calling out super glues and epoxies. They did have some difficulty in open ocean attachments, and we are working with them to work on technique. And that's a big takeaway that we've been learning, is that in open ocean, technique matters a whole lot. We also have a NOAA affiliate. So they are working in two depths. One at 60 meters and the other one at 200 meters, and doing reef repopulation at those depths, which was very interesting to me. But apparently that's there is something there. And their takeaway was, it works. Once it cures, it is solid. So that's another thing that we learned in this process, is because this CTAC is formulated with calcium carbonate and so highly loaded with calcium carbonate that the coral polyps actually love, and they grow over top of the adhesive much more rapidly than they do over epoxies or cyanoacrylates. So this kind of gets us into some of our learnings throughout the process. And yeah, what do we learn, April?
We've learned that it works fantastic in the lab. We've had multiple large groups say repeatedly that this is the best adhesive that they've used in the lab. We've had some of those same groups say they are struggling using it in open water, And they're also saying that we realize that there is probably application techniques involved here that we're learning, and we as Mussel Polymers are learning right along with our restoration practitioners how this works, because it is a new material, it is new technology. And so we also have found that it's great for gap filling. So there's lots of different.
That was in the Bahamas, right?
Yeah, I believe it was.
Yeah.
Yeah, they were putting SeaTac into holes with little fragments on top, and they were having success. They said it worked great. Different groups have used it as a primer because adhesive sticks to adhesive. That's worked for some groups. We found the less you touch it, the better. It wants to stick to plastic like crazy. And if you're wearing gloves, that can be cumbersome. So we're still learning techniques that way. And because you can use SeaTac as the structure, using an amount that matches what you're trying to glue, you can use a little bit and it will hold a whole lot. With that said, it may need some support while it cures, because once it's cured, it's permanent. It's 12, like you can't break it. The rock will break before the SeaTac will break, because it's like 12 pounds per square, 1,200 pounds per square inch of strength. It is so strong.
Yeah.
So technique, like Dave says, is huge. Stakes have been working really well. I had read just recently bamboo could be a great option. And metal has worked. And of course, again, you can just put it directly in the hole of the reef and apply coral.
Right. So this works on a whole wide range of substrates, as well as other stock, like plant stock or kelp or mangroves. We find it sticks to all sorts of rocks, to concretes. People are using this for structures and rockscaping, which is kind of very interesting. But at this point,
it's also great for seawater and freshwater, because water is the activator. Whatever is in the air, however humid it is going to be how fast it's activating.
Right. Absolutely. So, with that, like to open it up for questions, and, because we wanted to talk, and I can demonstrate more so that I'm with all the materials that we have. But I wanted to give a 30,000 foot overview of the Mussel Polymers journey. All right. So thank you very, very much, you guys. And I'm open for we're here for any questions.
Great. Thank you so much, David and April. That was amazing. That was so informative. And I'm sure our participants really loved listening in on this. So I'm going to open the floor for some questions. We already have a few in the chat. So I'm going to start going through these. And then if you all have any more questions, feel free to press the reactions button to raise a hand and unmute yourself to ask a question. Or if you're shy, you can also just put a question into the chat. So with that said, I'm going to get started. We have a question from David. It says, labeling indicates not safe to handle with bare hands. Evidently not correct. This concerned us when we read that regarding toxicity to organisms. Please clarify.
All right. So on this material, we have actually grown human cells on this material. This material in our biomedical actually stimulates stem cell growth. Okay. In this material, in order to, once it's cured, it is completely non-toxic. This is an isocyanate prepolymer heavily loaded with calcium carbonate. When you go through the governmental regulations, I have to put that warning on there because of the isocyanate prepolymer. Now, what's interesting is there are other countries that don't even consider this a hazard at all. When this isocyanate prepolymer cross-links, it becomes a completely inert thing. And again, we've got the evidence that the corals actually grow over top of this pretty rapidly. What's interesting is going through that regulatory process. One thing I don't have to do is the California Proposition 65 warning, which is, so this is not considered cancer causing in the state of California. And yet I have to put that warning label on. It's a regulatory thing.
Great, thank you for clarifying. So next question is from Pam. It's, what exactly were the open ocean difficulties in the Caribbean? The ones you were specifying a few slides ago.
April?
Yes. So some of the difficulties that we found is that when people are trying to apply CTAC in water, underwater, it's starting to cure immediately. We've got water layers that we're trying to navigate, like how do we get CTAC in the joint with the coral attached without it sticking on my gloves and to getting into the right spot. And that's where there's a million ways you can slice for technique right there. And that's where we're still learning is what is going to be a functioning application of CTAC underwater. We're still discovering that.
Right. So in one hand, we found that we can squirt this squirt it out. We can apply it to the reef and then stick a plate on top of that, and it works out fine. In the Red Sea, that tends to be a bit more particulate oriented, we have found that they actually need to get the nozzle right up onto the substrate and squeeze that right in between the joint and the reef itself. So this is where I'm referring to technique, because similarly, we've had people that have waited and tried to apply, and they say, hey, it doesn't stick at all. And what's wrong? How come you can get it to stick, but I can't get it to stick? And so we're trying to work with those people.
Yeah, it seems to be a lot more easier in the lab because you have a lot more controls there.
Yeah.
Exactly, yeah. So we have a question from Colleen. With our latest sample tubes, we plan to do some early tests, but we had, sorry, oh, Colleen, I think I just lost your question. In case you want to ask it just in person. But okay, now I found it. With our latest sample tubes, we plan to do some tests for both function and toxicity with Pacific corals and other applications at UCSC lab to help with the research. Just sharing, since seeing in the list that more toxicity testing is needed and it is a concern. Dave and April, is there a list of ingredients available?
Absolutely. I can send you an MSDS. Absolutely. Can send you a list of and anybody else who would want it. Absolutely.
Great. We have a question from Jen. Is there a thermal reaction as it cures?
There is no thermal reaction as it cures. The byproduct of the curing cycle is carbon dioxide. And so what you'll see if you're observing during the cure is small bubbles will form and will dissipate. So it's not a thermal reaction at all, unlike epoxies, which tend to be a thermal reaction.
We found that in the aquariums, it's not messing with the skimmers at all. It doesn't affect the pH. It's not burning the organisms that we're putting on it.
Thank you. We have another question from Arfan Hamka. What are the steps to use it in underwater, and do you have to use flat media? Can we attach the fragments on a vertical or inclined plane using this glue?
Yes, you can. With the caveat that it is a long set cure and it will need to be supportive if it's at a vertical or an angle until it's cured. So it may need to be zip tied, it may need to be
Right. Right.
Stay-
And so we are working on new product development for even a faster cure and stickier, tackier version.
Yeah.
So this is version 1. Version 2 is coming on out. But as April pointed out, it's a function of size and weight and angle that you're trying to attach. So if you're trying to attach a large coral dome, let's say, and you're trying to attach it upside down, you're probably going to have to support that for a while it's curing. Now, your working time with this adhesive is about 30 to 40 minutes. Your set time is between, I don't know, 2 hours, 3 hours, and it will fully cure overnight. So what I'm really, pointing out is this is a slow set adhesive. And if you're trying to attach something upside down without support, it will fall off. But one thing I will show you, this is a Lehigh River rock out of the Lehigh River. And we glued 3 of these rocks together. And I don't know if you guys can see that, but we glued 3 of the rocks together and then underwater, left it underwater for a week, came back and tried to break it. And what broke was the actual rock, not the adhesive. So once it's cured, it's cured. And you also don't need a flat substrate. You can, it's moldable. I don't want to use the word moldable, but yeah, as a gap filler, you can attach an irregular surface, attach it to an irregular surface.
I feel like it does even better when you do attach it to an irregular surface.
Okay.
Thank you so much. So I just wanted to be respectful of people's times. We are coming up on the hour. If you do have to jump off this meeting, the good news is that this is being recorded and will be posted onto the CRC EIG website in just under a few weeks. But if you'd like to get in touch with April or David beforehand, their emails are up here as well. But if you do have some time and you'd like to stick around, I do want to just respect everyone's questions. So I'm going to go through the rest of them. But again, no hard feelings if you have to jump off now, since it's almost.
And similarly, this is why I put up our email addresses, our phone numbers, and our website. So if anybody wants to reach out to us, we are happy to field all calls, positive or negative, and address, because we've been working at this now for 3 years, three and a half years. And so there's very few issues that we haven't been exposed to. Okay.
Thank you so much. All right, I'm going to keep going through the questions, but for anyone that needs to jump off, I just want to thank you again for your time, for joining in on this meeting. If you'd like to stay involved with the EIG, you can always email us at crc.eig@gmail.com to stay involved. So thank you so much.
Yep.
With that said, I'm going to ask another question from David Bushak. It is, we are testing it to glue live oysters and oyster shells to concrete wave attenuation devices we've designed to restore or form oyster reefs. Do you have recommendations for intertidal applications? Would you apply while substrate is exposed or immersed?
So intertidal applications. So a couple of things. In Tahiti, we have a group that is currently purchasing and using, and they're growing Maxima clams. This is not a reef restoration activity set. This is actually a hotel. and they are creating these structures for the hotel guests that have glass bottom rooms. And so they're attaching the C-tack to the outer shell of the bivalve and attaching those to other poles and structures. As dispensed, you want to have that in a low flow to no flow environment, 1-2 knots or so, because if you have a 5 or 10 knot current, you're probably going to knock that over. After about an hour to 2, you can move that into a higher flow environment. And then by the what I think about is current and tide change. And then by the morning of the next day, you'll have be able to withstand a storm surge. And then ultimately, when it cures, it's strong. I think I'm addressing that question. Brooklyn, do you think I addressed that?
I would say so. David, if you're still on the call, let me see if he still is on the call.
Yeah, I'm here.
Yeah, did we address your question?
Yeah, I think so. We used it on Monday and put it on our intertidal reefs, or a location where we have intertidal oysters in Cape May here in New Jersey. And we'll tell you what the results were. But we did it while they were exposed, because there weren't any recommendations about doing it underwater or not. It's also highly turbid, and you commented on turbid environments.
Sure.
That can be a little bit trickier. So
we can share, David, with you and anybody else. So we've got 2 groups that are working with oysters and oyster farming, and a third group that is working with scallop farming. And in the scallop, what they're doing is they're the way they're doing it now is drilling the scallop shell, and they have a snap, like a button, and they're snapping that onto a line. And then similarly with the oysters, they're doing this on lines and dropping the lines into the ocean. So what they're working with is using a dollop of adhesive on the backside, and they're doing it both in water and out of water. They're doing it both ways.
Oh.
thank you.
Okay, so
You're welcome to come down, by the way, and see what we're doing later.
Love to. I physically live in New Jersey, and so I would just jump right on down the Garden State all the way down.
great, we have a connection.
There you
So
go.
I'm gonna keep running through these questions again. If anyone has to jump off, that's totally fine. David and April, are we doing okay on time if we go through these?
Oh yeah, I'm
Okay.
here for your disposal.
Okay, great. So we have another question from Eleonora. Where has the product been used in the Red Sea?
Well,
I
go ahead.
don't know exactly. Go ahead, Dave. I just know
Oh.
Kaus has been.
It's in the Kaust area.
Okay.
Yeah.
Okay, so Saudi Arabia. Just
Yep.
joking.
Yes.
Saudi. Okay.
Yeah, but Saudi Arabia is such a big country. I don't know where they but we have a video, and if we can dissect that video.
I have to ask the
Absolutely.
restoration workers over there.
I can assume it's probably somewhere in Jeddah.
Yeah. Okay.
Great. Okay, next one. From Daniel DiMartini. What is the internal curing mechanism of the C-tack polymer? Does it rely on the cathcol and quinone formation?
Catechol and quinone formation.
Oh,
Actually,
sorry.
so we've got somebody who's familiar with the chemistry, and so the catechol actually speeds up that reaction, which and of course with the quinone, you're talking about the oxidative state of that catechol. And again, for the rest of you on the call, I know we're way over the top of the head as far as chemistry goes, but he's absolutely right that in this adhesive formulation with the isocyanates, moisture is the activator, and the catechol molecule acts as a catalyst, speeding up that reaction. And I believe that addresses his question.
I think so. And then what is the cure time?
Well, so this is why version 2 is coming out. So using a high molecular weight polycatechol styrene with a low poly dispersity, it cured in a 95/5 ratio. It cured solid walking from one lab to the other one for testing. In other words, I couldn't even get it to the second lab to test. We've dialed it back, and we're targeting a 5 to 15 minute cure time is what we're trying to dial in for that version 2.
That's great. And a question from Pam Gaffin. It's what kind of cost are we talking about?
That's another reason why this is, I'm not going to say delayed, but what I'm going to say, this is very, very important. When we started this project, mind you, I've got 6 labs, I've got PhD laborers, so I'm using high cost labor to produce. And a little bit of this stuff goes a very long way, is what I'm going to say. At one point, we were producing this at greater than $10,000 a kilogram, which is not doable as a bulk adhesive. So we have to drive this down the cost curve to make this in a way that would work in reef restoration. These materials are being sold at retail for $30 and $90 at retail. The reef restoration community is not considered retail, so these go for $20 and $60 per. Now, with the mitigating factor is increasing the speed of outplanting, but that answers your question directly. So yes.
I believe it does. And then one last question from Andrew Ross. Do all epoxies emit amines? I've seen that cloud only with the putties. Is it also and not visible with fluid epoxies?
Yes, that's correct. Yep.
Okay, great. Well, that finalizes our questions, unless anyone in the chat does have any more questions. But again, just want to be respectful of time. We're 8 minutes over. So I just want to thank you again, David and April, for being on this call. It was incredibly informative and inspiring, and I really look forward to all the change that can be done with these adhesives. So thank you so much.
Thank you to everybody. We really appreciate the time, and we're available for questions at any time.
Perfect. And you do have a few thank yous in the chat, so maybe just check on those. Can't read through all of them, but
okay, that sounds fantastic. All right, folks. Thank you very much.
We can stop the recording.